Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome back in lecture 11. Students, in lecture number 10 basically we covered the theoretical portion of punching shear design in flat slab system. And in this lecture inshallah we cover an example on it. So this is the same example as we started in lecture number 5. And from lecture number 5 to lecture number 8 we covered the flexure design and detailing of this example. Okay, and now we have to check the same slab system for punching shear design, whether it is needed a punching shear design or not. Okay, so let's start. We have to determine the effective depth. So our effective depth will be 9 inch because we have 10 inch, and just subtracting 0.375 is clear cover, and taking that 0.2 per half of that diameter. So this is 9 inch. B0 you already know for a square column, as in this example basically you see we have 14 inch basically square column. So for that purpose, when you have a square column, your B0 is nothing, it is just equals to, as you see here, this is the formula which is the general formula for both rectangle and square column, but here your C1 and CS both are same, that is 14 inch. So just put value here, you got your B0 value. Okay, now the next is the tributary area. So the tributary area, you see the area within these dotted line. Okay, this is the tributary area. Now you have to subtract, basically you have to find this whole area, and this whole area is nothing, this is just equals to L2 times L1. You already know L1 L2, that is equals to L1 equals to 25 and L2 is equal to 20. Okay, and you have to subtract this area. Okay, and how to subtract this area, you already know that you have to find out that black area within the column area. So this will be your basically your critical area, that is denoted by A0. And I already in lecture number 10 explained that how you determine that A0. Okay, if it is a square column, then you can easily determine that A0 area. This is just only C plus D whole square. Okay, divided by 144 to convert it into feet square. Okay, so this is in the case of a square column. So you see C plus D whole square, and they got the tributary area, and then you need to find out your shear. Shear is nothing, it is just only the effective that tributary area times the loading. After that, you have to compare your VU against your pi VC, that is the shear capacity of concrete. So to know about the shear capacity of the concrete, you have to use these four equations. Okay, so in these equations you know your D, that is 9 inch, B0 you determine it, and 92 inches. FC prime is 4, KSI 4000 you have to insert, and beta C is 40 you already know for and alpha is beta C is 1, beta C is 1, that is the longer side of the column to the shorter side of the column, and you know that is 1, and alpha is will be used as a 40 for anterior column. So you just need to plug all the values into these three equations. You got 156 from the first, 312 from the second, and 307 from the third. Okay, and after this you have to choose the minimum value, that is 156. Now 156 is governed. Compare this against VU and you see 190 cap, which is not good. This means that this example needed shear reinforcement. So to design this system for shear reinforcement, as already in lecture number 10 I explained, you have different options. Option number 1 which they are using is drop panel design, and you know how we can determine drop panel. So in drop panel, basically what we needed, we have to calculate basically the depth of drop panel. So you already know that let's say this is our drop panel. Okay, this is our drop panel, and here is the column, and you have to calculate this total depth. This is H, and you already know this depth, this is 10 inch. So your drop panel depth HD, we can say this is H minus HF, or you can say 10 inch. So now how you can determine this H? This can be easily determined from the same shear equation, this equation. as we see that this equation is the governing equation. This give you the minimum value of pi VC. So you just need to compare your pi VC against your VU. So as you see, pi VC contain D, so we will just calculate this D from this equation. Okay, just shifting all the values to the right, and we got our D value. So once you got your D value, you have to convert this into total H, and you just need to work. So you have to just 1.5 or 3/7. Okay, so you got your H value. So this is the approach. You see here they explain all in the same way, and once you see they compare, they find out the D, and they just add 1 inch clear cover. So they got 12 inch. So you have to subtract 10 from 12 inch. You just see you have a drop panel depth is a D. You can say this is HD, that is 2 inch. So if there is SEI criteria that this depth should not be less than, you can say HD, it should not be less than HF divided by 4. So you divide that by 4, you got 2.5, and add this is which governs drop panel, and that why we use HF equals to the thickness of this drop panel will be 2.5 inch. Okay, not 2 inches. And the sizes of the drop panel, you see this cantilever projection and this cantilever projection. Okay, and similar this cantilever projection and this cantilever projection. You see here this cantilever projection will be equals to 20 divided by 6, and this cantilever projection will be equals to 25 divided by 6. Okay, so it is clear from the diagram. Now you have to use 3.5 by 4.25 rectangle of drop panel having a thickness of 2.5 inch. So this is option number 1. Option number 2 is a column capital, and you all know in column capital what we need. We have to fix this angle with vertical angle, this angle, and you have to find this beta C. Sorry, this is denoted by C. Now how we can find out this C? The same way we compare the pi VC against VU. From this we determine beta naught, and once you got your beta naught, you see your beta naught for a square column equals to 4 times C plus 9, as 4 times, you already know beta naught equal to 4 times C plus D. So from this you will determine the C, because this is the size of modified column. Okay, so after getting this C, which comes out to be 19 inches. Now this means what? This means that the thickness of the critical, this one, remember this is now 19 inch. This is now 19 inch. So you see we have to use a vertical and similar vertical here. So what will be this cantilever projection? Okay, what will be this cantilever projection right now? So you know that, for example, if I draw things clearly right in this way, so this is basically C, the column size, that is 14 inch, and from 19 you have to subtract 14. Okay, it will give you 5 inches. So divide that 5 by 2, because half will be there and half will be that side. Okay, so this will give you 2.5 inch. So that cantilever projection now is 2.5 inch. So you have now a triangle, writing a triangle like in this shape. Fix this theta, and this side is 2.5 inch. You can easily, by trigonometry, you can find out this y equals to 2.5 divided by tangent theta. Okay, so for various values of theta, but remember this theta must be less than 45 degree according to ACI. Clear? So here you see that at the same calculation, 2.5 divided by tangent theta, let's say 30, then y will be this one. If theta using 20, so then y will be this one. Clear? So this is the design of column capital. After column capital, the next option, that is the third option, is the integral beams. And you already know the integral beams. What is an integral beam? You see at the place of column, we just use a beam, okay, an interior beam like a ceiling beam, okay. And in this ceiling beam, basically we have to determine the leg length of this beam, or you can say the length of the horizontal bar, and the design of these vertical stirrups. So just like a shear design, okay. Now basically we have to find this horizontal length, and we have to find this shear reinforcement. Clear? So for that purpose, you already know we use this equation, and the equation we already derived. And one thing very important, that whenever you are using, and already I explained this point in my lecture number 5, sorry, that whenever you are using an integral beam bent up bars, you have to half your strength of your shear, pi VC divided by 2. So this point is very important. Now you see here that divide the punching shear capacity of the column of the concrete, sorry, and it find out to be 78 kips. Now you have to use pi VC equals to 78 kip. Here they say that, let's say they are using number 3 bar as a stirrup, 2-leg stirrup, okay, 2-leg stirrup. As in one video, let me show you in this video. Here you have we have to find out the distance from the face of the column to this much. Remember, these bars are extended for a little bit smaller, for a specific distance that is denoted by LV, and then we have to place basically the vertical stirrups. Now the design of these stirrups is very important, okay. The design of these stirrups is very important. Let me show you the design of these stirrups. These are, okay. So you see here 1, 2, 3, 4, 5 and 6. There are 6 leg stirrups, and here in the example we assume that we are using 2-leg stirrups, mean that one leg will be here and one leg will be here. Remember, you have 6 legs, then you have to place 6 horizontal bar, and these bars are the same bars as we are using in the slab as a flexure reinforcement. So 6 bars in the top and 6 bars in the bottom. Similarly, we are using 2-leg stirrup, means we have 2 legs, so we need 4 bars, 2 in top and 2 in bottom. So we have to find out the spacings of these bars, okay. And the spacing of these bars is simple. We are just using the shear formula. As we already explained this formula, you already know in shear design of our beam. Here you see the drawing of the integral beam, and this looks like in this shape. And here you are see the specification 12. You have to use 12 legs or 12 number of rings, 1 or 2 at size at the rate of 3 inch center to center. And similarly, you see in this video that triple legs, you can say, in each way, means you have to place this kind of stirrup system 3 numbers that give you 6 total legs, okay. And here you see in the cross section, basically you see the design, okay, that you have to place 6 bars in bottom, 6 bars on top, and 6 leg stirrups. Clear? So we have to know this kind of design we need it. So let's say that assuming that we are using 2 legs, 2 leg will give you, remember, you already know from the shear design, 1 leg of number 3 equals to 0.11. So multiply with 2, you got 0.22. Now as you see in this picture, we have 1, 2, 3, 4 beams. So in 4 beams we have to place this 1 stirrup. So that's why you have to multiply this area further by 4. Then we have to find out the spacing. You already know this formula. This is the shear formula, and D will be now is 9 inches. Okay, AB is 0.8, and you just plug all the value. Now this 6 is very important. This 6 is very important. The 6 is basically, remember, whenever you are using the integral beam, okay, what are the ACA provision? The ACA provisions is that your your slab thickness, effective thickness must be equals to minimum. It must be minimum equals to 6 inches or 16 times the diameter of your shear reinforcement. So this is very important, and this is the you can say condition of basically your ACI. Remember here, least of 6 inch or 16 times. So this will govern. Okay, you don't need to use that 9 inch. Okay, and you must confirm this sentence as well. Okay, this will be 3 inch, and here you also got 3 inch. So this means that we have to place number 3. We have to place number 3 at the rate of 3 inch center to center. Okay, this is our here in this video you see they are using basically 3 inch center to center as well, and 6 leg stirrups, but we are using 2 leg stirrups at the rate of 3 inch center to center. So this is important, very important. This is all about shear design. Now we have to find out the leg length, mean that for how much distance we have to extend, these horizontal bar. And I already derived this equation in lecture number 10, this equation. Okay, the derivation in front of you, you can do it. We have to find out this LV. So to find out LV, we need beta naught, and already we calculate beta naught is 111. Okay, 111. We already calculated this beta naught. Okay, so beta naught is equals to this one, 111.26. You compare that equation with beta naught, or you can say placing beta naught here, 111.26 equals to this equation, 4.24 LV minus plus 1.88 C1 or C. So C is 14, and you just need to shift this value here and leaving LV. Okay, 111.26 divided by this 4.24, okay, and minus 1.88, and this C is 14 inches. Okay, so after doing this you got this 20 inches. So once you got 20 inches, this means, let's say we are using 2 feet, like 24 inches. Here you see. So this means the bars now will be extended from the face of the column for a distance of 2 feet. Means that 4 by 4 feet in this side and 4 by 4 by this side. And remember, this is very important that from the critical parameter, okay, from the critical parameter, the stirrups should be the stirrups from the face of the column, it should be placed within a distance of this distance 24, or you can say 24 inch minus d by 2. Okay, this is very important, d by 2, I think so. Yes, d by 2, 5 inch. So now the stirrups distance will be 19 inch. You have to place stirrups in 19 inch. Remember, let me show you like in this way. Let's say this is the face of your column. So you have to place the stirrups within 19 inch. And you just leaving that bar for 5 inch as, okay, you see just in this video you see the bars are, remember these bars you see, they are leaving for a distance of d by 2. Okay, there is no stirrups in distance of d by 2 from the last end. This is very important. Okay, and you see the final design. Number 3 at the rate of 3 inch center to center slab you see, and this is the cross sectional beam for number 5 bar. Okay, and this ends of the design of shear reinforcement. Now you have to place basically from the face of the column 4 bar, and remember stirrups at the rate of 3 inch center to center. Similarly to this direction, similarly to this direction, and similarly to this direction. For these edge column, for these corner column, you can do the same thing. You need to find out your beta naught. You need to find out after after getting beta naught value, here remember this is the H column, and how we can determine it for H column. So I already explained this in my lecture number. This is for corner column. This one formula will be used, okay, and this one for H column. This is for H column, okay. Here C1L and C1S will be 14 inches, okay. And yes, similar beta naught, once you calculate it, you have to use those three equations and you find out your pi BC. You need to find out your VU. Here VU is also different. Remember, this one will be your VU, okay, and this dimension is 20 feet, sorry, and this one is now 12.5. So 12.5 times 20, it will give you the whole area A, and A naught you will easily calculate from that formula. I already write down that formula in my lecture number 10. So your tributary area will be AT is A minus A naught. Okay, you got your tributary area, and then you got your VU, WU times tributary area, and you just compare that VU against pi VC, okay, pi VC. So if it is less than, so then you know you need not to use any integral beam or drop pen or column capital. If it is greater, then you have to design, okay. Similarly for this corner column you can do the same thing, but here the tributary area, this whole area in this case is 12.5 in this direction and 10 in this direction, remember. So your A will be how much? 12.5 times 10 feet, sorry. This will give you whole area, remember. And similarly A naught, you can determine it. A naught will be, I already explained, write down this formula in lecture number 10. C, remember, C plus D by 2 times square, okay. In this case it will be square because you have two sides which is equal. One side C plus D by 2 and this side is also C plus D. So you just to square it, you got A naught, and your tributary area then A minus A naught. Okay, so you can do this calculation by yourself. This winds up your design of your flat slab system. If you have any question, any suggestions, okay, you can share with me. Thank you for watching. See you in next lecture.